Alright, welcome back. In this video, we're going to be talking more about rational functions. But I think before we start, I'd like to recap what we talked about in the last video. So we started off with a discussion of the graph of y equals 1 over x. And we made a nicer looking one than this, but we saw that it kind of looked like this. And then we talked about asymptotes. We were talking about domain and range too, but an asymptote was a line that the graph came really close to but wasn't able to actually touch. Or that the farther the graph went along, the closer it got to the line. Probably a better description. So we saw we had a vertical asymptote here that was caused by, the fact that we can't divide by 0. And if we put numbers that are really close to 0 in for x into that equation, we get values of y that are really big. And then we also had a horizontal asymptote here on the x-axis. That was y equals 0, because 1 over x, that could never really equal 0. But maybe a better description of that horizontal asymptote would be the bigger x gets in positive or negative direction. Okay? If we put in a really big number for x, 1 over x is going to be a really small number. And that's going to be something that'll last with us a little bit longer. But that was the graph of y equals 1 over x and the asymptotes. But then we looked at related graphs, something like this function, and we saw that the 2 and the -3, they just ended up kind of moving the graph around and changing the asymptotes. That all really went back to the ideas of domain and range that we've been talking about all along in this class. Now today I wanted to start you off with a quick example. F of x equals x squared minus 1 over x minus 1. And if you're thinking well, man, I feel like I could simplify that a little bit, we can, and we're going to. But first, I want to just make a table of values for this function. So I won't make you watch me do all these computations, but if we plug in x into x squared minus 1 over x minus 1, this is what we're going to get. And I just might simplify these and say, okay, f of -2 equals -1, f of -1 equals 0 divided by 2, or -2, which is 0. F of 0 is going to equal 1, because -1 divided by -1 is -1, or is positive 1. This 0 divided by 0, I'm going to remind you that division by 0 is undefined. Okay, so this does not exist. And that's going to be important for us. I'm just going to say D and E. Okay, but f of 2 is equal to 3, and f of 3 is equal to 8 divided by 2, which is 4. Okay, so I've got a table of values, and I'm noticing a pattern here. It looks like f of x is equal to x plus 1. It's, the output is always 1 bigger than the input, so it feels like it's, f of x equals x plus 1. But let's, try to simplify this. And if we wanted to simplify this function, we need to factor the top and factor the bottom. Now the bottom's not going to be able to be factored. There's not really anything we can take out of x minus 1, but the top, x squared minus 1, that's a difference of 2 squares. Okay, so I'm going to say x squared minus 1 is x plus 1 times x minus 1. And I'm going to be dividing by x minus 1. Okay, and we did this at the beginning of this unit, right? We simplified things like this. So I could go in and I could say, okay, cross off these, because, basically x divided by x minus 1 divided by x minus 1, that's just going to be 1. And so it's going to be 1 times x plus 1 for all x except for when x is equal to 1. So I'm going to say that this is equal to x plus 1 as long as x is not equal to positive 1. But that's kind of what we were seeing in the table of values. So let's just kind of sketch a graph and see what we're looking at here. So if I went to graph this thing, it just looked like the graph of y equals x plus 1, and we know how to graph that. There's a line with slope 1 and intercept 1, all the way until x is equal to 1, and then there would just be no graph there. Okay, and so we're just going to represent that by putting a little open circle. And then the graph would resume doing its normal thing, y equals x plus 1. Okay, and that's what the graph of this function is going to look like. It's going to be a regular function with a hole in it. And that's really one of the main things I wanted to tell you about today was, what can cause a hole in the graph. In pre-cal and in calculus we'll talk about, continuities, and we'll call this a removable discontinuity, but it's important in algebra 2 that you know that this can happen. When we have, common factors on top and bottom, really what caused this was this cancellation right back here. Okay, all the way back to where we canceled x minus 1 over x minus 1. So the rule in general is going to be The x-coordinate of a hole in the graph is the zero of the canceled factor. So it's whatever caused us to cancel off the, what am I saying? To get 0 over 0. Yeah, that's the other thing. It causes 0 over 0, and we see that because of the canceled factor. That's going to be the x-coordinate. And we obtain the y-coordinate by plugging that x-coordinate into the simplified version. So notice if I plugged x equals 1 into the simplified version, y equals x plus 1, I'd have gotten 2. And that's what I'm seeing right here, y-coordinate of 2, or so it looks. And so I'll just copy that rule in here. There you go. So let's move on. Let's graph a couple more of these. The first one's going to be x to the 3 plus 2x to the 2 divided by x plus 2. And what you're going to see with these problem types is a lot of factoring. And I told y'all throughout the course that factoring was going to be the type of thing that we're going to do over and over again throughout the year. And this is one of those situations. So I'm going to start by just factoring the expression. And with a lot of these, we'll need to factor both the top and the bottom. But again, the bottom is not going to be something I can take anything out of. I'm seeing a greatest common factor in x to the 3 and 2x to the 2. It's those x's. So I can factor out 2 powers of x from the top and be left with an x and a plus 2. And then I'm dividing by x plus 2. So I'm going to kind of simplify by canceling off those factors. I'm going to say that this is equal to x squared with a hole at x equals negative 2. And I'm saying it's going to happen at x equals negative 2 because it's the x value that causes the canceled factor to equal 0. So if I look at that and I say, okay, I'm looking for the value of x that makes x plus 2 equal to 0, that's going to give me x equals negative 2. And that's why I'm saying that. Okay. But if I wanted to sketch the graph, okay, I know how to sketch the graph of y equals x squared. It's just the regular old-fashioned parabola, and we've sketched that a bunch of times in this class. So it's just the regular parabola, but it happens to have a hole at x equals negative 2. So we're just going to decide wherever we think negative 2 is. Decide there, and just kind of try to draw the same graph over here. Put a hole in it, and then rest of the standard parabola. And it's a pretty decent sketch, especially if I was to label my axes. And so that's going to be the sketch of f of x. And just y equals x squared with a hole at x equals negative 2. Now if we were asked what the y-coordinate of the hole was, okay, we would plug negative 2 back into the simplified version of f of x, that is x squared. So I'd say the y-coordinate of the hole is going to be negative 2 squared. That's positive 4, and so I can just put that label right there. This next one's going to be largely the same. I'm going to start by factoring and canceling. Okay, there's nothing really to be done from the top, so I just got an x minus 3. But in the bottom, I've got an x in common to both, so I'd say x times x minus 3. And then I see x minus 3 on top and bottom, so I can cancel those off, and I'm left with a 1 on top if I don't have anything left. And so this is going to equal 1 over x with a hole at x equals 3. And again, just to be real clear, I'm claiming that there's a hole at x equals 3 because x equals 3 is the value that makes x minus 3 equal to 0. And so I can go in and sketch a graph. Because we just learned how to sketch the graph of y equals 1 over x just in the last lesson. But we're just going to standard 1 over x, but wherever we decide 3 is, there's just going to be a hole in the graph there. It's going to continue doing its normal thing. And over here, otherwise unchanged, right? Because the behavior of the function is only going to be affected at this x value, at x equals 3. Now we're going to talk about a different type of function. A function that's kind of like linear on top and linear on bottom. And we're going to eventually just rewrite this and see that it can be written as something that we'd be really familiar with. And I can see that this can be simplified. Like I see that there's a factor of 3 on top and bottom. But for the sake of the example, I'm going to leave it the way it is. So we're going to start by finding the x-intercept of this function. And we're going to do that by setting y equals 0. Okay, so that means that f of x needs to equal 0, and that's 12x plus 6 divided by 3x plus 3 equals 0. Now, in the future, I'm going to probably just say, okay, a fraction only equals 0 when its numerator equals 0. I may have already alluded to that, but for now, I'm going to just solve this maybe the most obvious way, and that would be by multiplying both sides by 3x plus 3. So I'd say 12x plus 6 is equal to 0 multiplied by 3x plus 3. But we know that 0 multiplied by anything is just going to be 0. So 0 times 3x plus 3, regardless of what x is going to be 0. So I'm just going to get rid of it. And I'm going to say, all right, 12x plus 6 needs to equal 0. So I'm going to subtract 6 from both sides. I'm going to say 12x equals negative 6. I'll divide by 12, and I'll get x equals negative 6 over 12, which is negative 1/2. I could also find the y-intercept. I'd find that by plugging in x equals 0, so I'd get, f of 0 equals 12 times 0 plus 6 divided by 3 times 0 plus 3. And that's going to end up being 6 divided by 3, which is 2. You might also be interested in like the domain or the vertical asymptotes to this graph. And that's not going to be changed by the fact that we've got, some kind of x and something else going on up top. We're still going to find the domain and the vertical asymptote by investigating, when does the denominator equal 0. Okay, so I'm thinking, okay, well, as long as 3x plus 3 is not equal to 0, then f of x will be defined, right? The only thing that could go wrong here would be dividing by 0. So I'm going to subtract 3 from both sides and divide by 3. And I get, not equal to that. And that's negative 1, so my domain is going to be all x that is not equal to negative 1. As a result, I can say the vertical asymptote to the graph of f is going to be x equals 1. Now, if we wanted to investigate the range, or the equation of some kind of horizontal asymptote, I think we'd be best off by rewriting f of x. So what we're going to do is we're going to use some polynomial long division. So we're going to just, kind of rewrite f. We're going to do that by taking 12x plus 6, we've done this before in this class, and dividing it by 3x plus 3. I think that this time you might like it a little better, because if we're just dividing linear over linear, what we're going to see is it only takes one step. Okay, remember the first step is we take the thing on the outside and we say, okay, what do I multiply 3x by to get 12x? And that would be just a positive 4. And then I go back through and I multiply 4 times 3x plus 3, and just got to remember to distribute the 4 over the 3x and the positive 3. So I've got 4 times 3x is 12x, and 4 times 3 is 12. Okay. Okay, I'm remembering didn't call that x equals negative 1, and also I copied the function down differently from how it is in my notebook or how I did it in lecture in class. So if you're, confused about that, I'd say just change it to 3x plus 3, and the example will still work. Okay, so I've multiplied that through. I'm over here. I'm trying to simplify, so I'm going to subtract. Whoops, wrong color. I'm going to subtract 12x plus 12, and I'm going to get, 0, and then 6 minus 12 is negative 6. So my remainder is going to be negative 6, so minus 6 over 3x plus 3. Okay, so that's great. We can just rewrite f of x as that quotient. And this will make us much more able to find the range and, kind of think about the equation of a horizontal asymptote. Okay, the range is going to be y is not equal to 4, because now that I've written it as, 4 minus 6 over 3x plus 3, I know that that 6 over 3x plus 3, that's never going to equal 0, because I got 6 on top. So the range is going to be y can't equal 4 minus 0, so y is not equal to 4. And then as a result, I would say that the horizontal asymptote would be the horizontal line y equals 4. And now with it written like that, I think we'd be able to sketch the graph of this thing. Okay, we've got vertical asymptote, horizontal asymptote, we can fit that in. We know that it's going to be kind of like a negative 1 over x type graph because of the minus 6 over 3x plus 3. I might point out that we could simplify that a little bit farther and I'll say, all right, maybe divide top and bottom by 3. So 3 times 2 divided by 3 times x plus 1. And so, once we cross those off, it would be like 4 minus 2 over x plus 1 if you're interested in like kind of the scale factor there. But let's just plot this like we know how. So I plotted the asymptotes, and now I know this is going to be kind of like a negative 1 over x type graph, so it's going to be looking like this on that side. Then on the other side, I might need to be a little bit careful about my intercept. So my y-intercept is positive and my x-intercept is negative. Okay, well that's probably not totally unexpected that the graph might go like that. Okay, and to just kind of label the points as I had before. Okay, we said x-intercept was in gray, y-intercept in green. It looks believable. At least the signs are right. Okay, but that's us sketching a graph. Alright, so the message here is when you are confronted with f of x equals linear on top over linear on bottom, okay, ax plus b over cx plus d, what I want you to do is, use long division to rewrite in a better form, okay? I think that's going to be the best course of action for us if we rewrite it, some number plus some other number over cx plus d. We have a much better chance of graphing it in this class. All right, now I want to talk about what would happen if we had quadratic in the denominator. Okay, so consider the function g of x equals 1 over x squared minus x minus 2. If I factored the bottom, I'd get x minus 2 times x plus 1, because I would be looking for two numbers that multiplied to negative 2 and added to negative 1. And that would mean that I'd have vertical asymptotes at x equals 2 and x equals negative 1. Okay, so I'd have two vertical asymptotes, x equals 2 and x equals negative 1. So I'm just going to try to sketch the graph of this thing. I'm proposing that the horizontal asymptote to the graph of g is going to be y equals 0. And that's because, we're really thinking about the end behavior of the function, and we know the end behavior of the denominator. The denominator is a degree 2 polynomial with a positive leading coefficient, which means as x approaches infinity or negative infinity, that denominator is approaching infinity. And if we take 1 and we keep dividing it by a bigger and bigger and bigger number, that's going to leave us with a smaller and smaller and smaller quotient, really without limit, right? And we could say that we're going to get as close to 0 as we like by just taking sufficiently large values of x in either the positive or negative direction. And so that's why the horizontal asymptote of this thing is going to be y equals 0. Okay, past that, okay, we're going to need to plot some points, I think. But before we do that, I think it would also be important for me to point out that this graph is not going to have an x-intercept. That's not going to be possible at all because the numerator is 1 and the denominator is variable, right? So we're never going to have 0 over non-zero, which would be what we would need for g of x to equal 0. Okay, so there's not going to be an x-intercept. I'm going to put that in there. No x-intercept. Okay, so now I'm going to just try, what happens when I plug in 0? Okay, so g of 0 is going to equal 1 over 0 squared minus 0 minus 2. So that would be 1 over negative 2 is negative half. Maybe I'll just plot that right there. And what I'm telling you is, okay, I've got to stay, and I've got to respect these vertical asymptotes. They cannot be crossed. But also there's no x-intercept. So that means that the graph, in some way, has to look like this. Okay, because we have to stay away from the asymptotes, and we can't touch the x-axis because there's no x-intercept, so it must look like that. And then I might try something bigger than 2, like, maybe g of 3. And I'd have 1 over 3 squared is 9 minus 3 minus 2, and that's 1/4, which is a positive number. So maybe I just put that right here. And so again, there's no x-intercept. I have to respect the vertical asymptote. There's going to be a horizontal asymptote eventually of y equals 0, so the graph's going to look like this. And then if we go and we plugged in something more negative than negative 1, like, negative 2, I'm going to need a little bit more room, yeah. That would be 1 over negative 2 squared is 4 minus negative 2 minus 2. Okay, so that's another 1/4. So I'm looking at the same. And the same logic applies. No x-intercept. Vertical asymptote must be respected. Horizontal asymptote, eventually we have to get there. So the graph's going to look like this. But I don't think I'm going to ask you to do a whole lot of these in this class. I just wanted to show you like what can happen and how we can kind of like just piece our way through to a graph based on pretty limited information. All right, now I'm going to wrap up today's discussion with the bigger on top scenario. And this is a topic that we're really going to dive into next year in pre-calculus, but I want to kind of show you what's going on with these. So if I do polynomial long division on both of these rational functions that I've got that are going to end up giving you kind of something weird, you'd end up with this. We could rewrite these functions as, like x plus 1 plus 2 over x minus 2, or x squared plus 1 over x plus 1. And what that means is that we could look at it, let's kind of write it a little bigger, y equals x plus 1, like a linear function, plus, a rational thing that's going to have a vertical asymptote at x equals 2, because of the 0 in the denominator. And then this one, we could write as y equals x squared, like a quadratic function, plus a little rational part, 1 over x plus 1, that would have a vertical asymptote. Now, if I pulled in a Desmos window, we'd see that in some ways it looks like, a somewhat typical rational function. We're seeing, vertical asymptote, kind of weird shape of the graph. But if I zoom out, what I'm really seeing is just, other than the fact that I've got a vertical asymptote on this red graph, it's really a linear function. And so and the farther away I go from the vertical asymptote, the closer it gets to probably the line, whatever that function was. What was it? I think it was y equals x plus 1. Let me go back and look a second. Yeah, y equals x plus 1. And if I turned that one off and turned on the other one, what you'd see is what I was saying, it got kind of a parabola-shaped asymptote. So what I've got here is really like the graph of y equals x squared, except for a brief interlude where it's getting really impacted by that 1 over x plus 1 that I saw it had in it. So that was just something I was going to show you could happen. But just to reiterate what I've been saying, in our Algebra 2 class, we're mainly concerned with y equals a plus b over cx plus d, something that looks like that, or linear over linear, the thing that we folded in today. And I suppose we're interested in graphs that have holes in them, but that's kind of separate from the discussion of rational functions that we've been having otherwise. All right, that's all I got for you in this video. Thanks for watching.